Hello, and welcome to this introductory video on the idea of magnetic flux. In previous videos, we've introduced the idea of a magnetic field. We know that it can exert forces and things like that, but turns out that there's even more that a magnetic field can do. In order to access that next level of complexity, we need to first introduce this idea of magnetic flux. So let's go ahead and do that. What is magnetic flux? Well, to sort of set the stage, a lot of times what we'll be dealing with is some sort of nice magnetic field. Let's define one always coming out of the board. And it turns out that an interesting quantity to consider is sort of how much magnetic field passes inside some surface. So this surface will have some area A. There's this magnetic field B. And what we'd like to know is how much magnetic field is sort of passing through that surface. And that is what flux measures. It tells you the field that is passing through some area A. Now, turns out, of course, that this gets a little bit more interesting. As I rotate this, the field that actually passes through is going to change, because even though the shape is a square, as I rotate it, it becomes looking more and more, starts looking more and more like a rectangle. Right? And if I make it exactly so that I've rotated it 90 degrees, it now looks like a single line through here. And at that point, there's no flux through it because it's just not actually presenting any surface area. It's just a line. It has no width. Okay, so I need to know something about really the projected area of that shape, not so much its absolute area, in order to talk about how much field is really passing through the surface. Okay? So a better way of saying this is it measures the field passing through some surface, which is talking about the field through its projected area. And the way we do that projection is by adding a cosine of the angle. So the flux, which we represent by the symbol phi, is equal to the magnetic field B times the actual area of the thing times the cosine of the angle between the area and the magnetic field. Now that may or may not make sense. In fact, it shouldn't make sense, because area is, of course, a scalar, but we can define an effective direction as the normal to the surface. Okay? And normally, pardon the overuse of the word normal, as the normal, what we mean is the way out of the surface. So if this was actually a three-dimensional box, then that would have very nice meaning. For a single plane like this, doesn't really matter which one you take, but the flux through that surface we take as B times A times the cosine of the angle between the magnetic field and the outward normal of the surface. The units for that thing are simply Tesla times meter squared, Tesla from the magnetic field, and meter squared from the area. Okay. This is going to be a very important quantity, and we'll see why in later videos. Another nice conceptual way of viewing what magnetic flux is doing, because now we've got this weird projected area thing, is it's basically just counting how many field lines actually pass through the surface. As I rotate it, as I decrease that projected area, of course I'm getting less field lines through there. So that's what that expression is capturing. And the nice idea conceptually is I'm just counting how many field lines pass through the area. Some food for thought to make sure you're really understanding this, and some key concepts about electricity and magnetism. Bearing in mind that there is that cosine of the angle between the magnetic field and the outward directed normal, true or false, the magnetic flux through a closed surface is always zero. And you can extend the magnetic flux to just talk about the electric field lines passing through a surface. So you can define an electric flux. Is that electric flux through a closed surface always zero? Think about those. I'll tell you right now, one of them is true and the other one is false.